Hello class. Today we're going to be talking about diluting solutions. This is a very important part of working in a lab setting. In fact, here at the school when we order chemicals, let's say we order an acid for example, they will come in a jug like this. It is clearly more efficient to ship a smaller volume that is much more concentrated, and then we can dilute it here at the school. But I would never give a student this concentration. This is 12 molar hydrochloric acid. This is extremely concentrated, and if you were to get it on your skin, it would give you severe chemical burns. So what we do to prepare hydrochloric acid for a lab is we will take that 12 molar, figure out how much solution we're going to need for the lab, then we dilute that 12 molar down into our usable stock. So maybe it's, 1 molar hydrochloric acid. So we would take that 12 molar and we would add water until we reach that 1 molar point. The question is, how do we figure out how much water we need to add, given the final amount that we want to make? How much of our stock are we actually going to use? How much volume of that will I add in order to achieve our desired concentration? So that's what we're going to be exploring today. So first up, when you are diluting something, this is relative. These terms concentrated versus dilute. If we look at these three solutions here, solution A, B, and C, you can make some judgments of the concentration relative to one another. Which of these would you say is the most concentrated? Well, clearly it's A, right? The one that has the most amount dissolved per unit of volume. Which one is the least concentrated, the most dilute? That would be solution C, right? There's only 1 gram per 100 mLs. That is the least amount of solute per unit of volume. So again, these terms I'm going to be using, dilute versus concentrated, these are somewhat relative terms and relative to something else. So again, A is concentrated, C is dilute. Now solution B would be considered dilute compared to solution A, and it would be considered concentrated compared to solution C. So these are relative terms. Now how can we make a solution less concentrated? Well, we can add solvent. Super easy way to make it less concentrated. Now, the number of moles of solute does not change when the solution is diluted. And that makes perfect sense. If we have a certain amount of solute in our beaker, right, we dissolved, say, 29.22 grams of sodium chloride, by adding more and more water, are we changing the number of moles that we dissolved within that solution? No, we're not, right? We're making the solution more dilute. There's going to be less grams of sodium chloride per unit volume of water, but we're not changing the amount of sodium chloride within that solution. Whether we dissolve that 29 grams in 100 mils or a liter, 1,000 mils, if we boil all the water off, we're still going to get back the same amount of sodium chloride. Now keep that in mind. That is super important for what we're going to talk about next. So again, the number of moles before dilution is going to be equal to the moles after dilution. The moles does not change. What does change is the liters of solvent. So let's explore this through an example. Okay, so I'm going to show you perhaps the harder way of doing it right now, but then I'll show you a little trick, an easier way. So what do we know? The moles before is equal to the moles after. So we could figure out the moles before, make that equal to the moles after, and we can use our concentration formula to determine the final volume. Now, if you didn't follow that, we're going to go through it step by step. So how many moles of NaOH do we have prior to dilution? Well, that's going to be, remember, our concentration is our moles over our volume. So our moles then is going to be our concentration times our volume, or 4 molar times 3 liters, which gives you 12 moles. So before we diluted, we have 12 moles of NaOH. Is that the same as the amount we're going to have after dilution? Yeah, no, that is, right? It's for sure going to be the exact same. We're just adding water. We're not changing the amount of NaOH. So, if we know that this is the moles before and after, right? It's the same value. We know our final concentration. Well, we can solve for V to get our answer. So if I solve for V here, our volume then is equal to our number of moles divided by our concentration, which is going to be, well, we have 12 moles. This is going to be divided by our concentration of 2.5 molar. I chose easier numbers. That's 4.8-ish. 4.8-ish liters. Alright, so that is the final volume of our diluted solution, right? This is the final volume of our diluted solution. Are we done? Are we done? The answer is no, we're not done, because we have to figure out the volume of water that must be added, right? The volume of water that must be added. This is our final volume of our solution, our entire solution. So to figure out how much water we must add, we have to subtract our original volume. So if we subtract our original volume, we find that 1.8 liters of water was added. So to prepare a 2.5 molar solution from a 4 molar solution, of which we have 3 liters, we must add 1.8 liters of water in order to achieve that concentration. Alright, so let's now look at perhaps the easier way of doing it. For those formulaic thinkers out there, this way is probably going to be a little bit more familiar for you. Let's figure out this easier way. Let's derive the formula. So if the moles before is equal to the moles after, one can derive the following. So we know that our moles is equal to our concentration times our volume per the concentration equation. And I'm going to label these C1 and V1. And this here represents our moles before, our concentration before, and our volume before. And I'm going to say here N2 is going to be equal to C2V2, where this represents our moles after, our concentration after, and our volume after dilution. What do we know about our moles? Is our moles before going to be equal to our moles after? The answer is yes, right? The number of moles before is going to be equal to the number of moles after. Therefore, right, we can say that, well, what is N1 equal to? That is equal to C1V1. And what is N2 equal to? C2V2. This here is going to be your dilution equation. If you are given a dilution problem, you can use this equation here to solve. Let's think back to that previous example. Let's plug in for what we know. So what was our initial concentration? That was it 4 molar? Yeah, 4 molar. So our initial concentration was 4 molar, and how much of that solution did we have? We had 3 liters. What was our final concentration? Well, our final concentration after dilution was 2.5 molar, and our final volume is a question mark. We know what it is because we solved for it already, but let's see if we get the same answer using this equation. So I solve for V2. V2 is equal to 4 molar times 3 liters over 2.5 molar. And again, we get the exact same answer. 4 times 3 is 12. 12 divided by 2.5 is 4.8 liters, right? We have to now subtract that initial 3 liters because this is your final volume of solution. And we see that you get the exact same answer using this equation. So it doesn't really matter which way you solve it. If you're more comfortable solving it stepwise, go for it, right? If you want to think back to the last way I solved it, maybe that's more reminiscent of stoichiometry for you, you go for it, right? You can solve it either way, it doesn't matter, but most students do find this way much easier. All right, so here we have our concentration before dilution, concentration after dilution, and this will always work for any dilution problem. Let's put it through its paces. Let's do a couple examples. So calculate the final concentration when 75 milliliters of water is added to 25 milliliters of 8 molar hydrochloric acid. So what are we given? What are we given? So we are given a volume of water that is added to our initial solution. So we know that our concentration initially is 8 molar. We know that our volume initially is 25 milliliters. We know that our final concentration is what we are looking for. We don't know what that is. And we know that our final volume here, be careful, it's not actually 75. What did we do? We added 75 milliliters of water, which makes our final concentration 25 plus 75, or 100 milliliters. Now, unlike before, since our equation has volume on both sides, right? But if I try to isolate C2 here, it's going to be V1 divided by V2. Since that's the case, you could actually leave your units in milliliters. I would recommend you always convert to liters. Just get in the habit of doing that. But as long as your units of volume are the same here, it doesn't actually matter. It doesn't need to be converted. You will get the same answer. But again, if that sounds confusing to you, always convert to liters. It is the safe bet. So, what is the answer then? Well, we need to solve for C2. So if I isolate C2, I get C1 V1 over V2, which is 8 molar times 25 milliliters, or 0.025 liters, divided by 100 milliliters, or 0.1 liters. What is 8 times 25? 8 times 25 is 200. 200 divided by 100 is 2. And if you think about it, that makes perfect sense. What did we do to the volume? We increased it by a factor of 4. As a result, what happened to our concentration? It decreased by a factor of 4. These are predictions you should be making. All too often, students, again, suffer from formula fixation, where they plug it in and then they solve and they mix up one of their variables, and then they'll all of a sudden tell me they have 32 molar as their final concentration. Well, think about that for a second. We added water. How could your concentration have gone up? So really critically assess those numbers as you go through the problem. All right, let's do one more quick example. What volume of water must be added to 150 milliliters of a 5 molar solution of sodium hydroxide to make a 2 molar solution? So we're making a 2 molar solution from a 5 molar solution, so we're going to be adding some water here. We know initially that our concentration is 5 molar. We know that our volume initially is 150 milliliters. We know that our final concentration is going to be 2 molar. And we know that our final volume is what we are looking for. So again, let's solve using our equation. C1V1 is equal to C2V2. And we have to isolate V2, which means that when we isolate V2, and here, again, I do recommend you always convert to liters. This is 0.15 liters. And if you didn't convert to liters, what would be the units of your answer for V2? It would still be milliliters, right? So here we have C1V1 over C2. This is 5 molar times 0.15 liters over C2, which is 2.0 molar. And this gives us a final volume of 0.375 liters. Now, are we done this example? Is that our final answer? Is it 0.375 liters? What do you think? The answer is no. What does that number represent? 0.375 represents the entire volume of your final solution. How do we figure out the amount of water we added? Well, we have to subtract our initial volume. So how much water did we add? Well, that's going to be 375 liters minus 0.15 liters to give us a final concentration of that would be 157,225 liters. So we had to add 0.225 liters or 225 milliliters in order to achieve our final concentration. So that is all for today. If you have any questions, do not hesitate to ask. Have a wonderful day.